Thank you for coming out. We know that there is a lot of choices. Next slide, please. So next, okay. So ADIOS had, no, previous. So ADIOS has a lot of contributors, and it's something that's been around a long time. So, again, when we talk about ADIOS, there are a whole bunch of scientists and engineers and people from all different fields who have contributed to this project. So we love when we have different people contributing. We think it's great, and we hope that for this, please tell us what to do, what you would like. Tell us if you know ADIOS, what's good, what's bad. Next. So, again, if you don't know what ADIOS is, we will thank many sponsors, but ADIOS is a high performance publish subscribe framework for IO. And in the picture on the right, that what it does is it connects applications together, from applications to storage, going to and from. It connects to different types of devices, from sensors. And in this presentation, you're going to hear from a lot of world-leading scientists who will tell you about their science and about what ADIOS has done. But when we talk about ADIOS, the figure that's in the middle, the middle part of the bottom almost, it's that ADIOS has what we call all these different engines optimized on different types of solutions, so that it's not just a one-fit-all. So the point is to get an easy-to-use API that has different levels of resiliency for these different engines to make things go. Next. So again, tell us what you want. Be vocal. I know some of the speakers can be very vocal to us. So the more vocal you are, the more feedback, the better that we can make this. So if you want a new engine, maybe there's something out there from the ECP community or for somewhere else that you can say, incorporate this into ADIOS. We want to tell you where we're going. We want to tell you all the things that have been done. Make sure you ask questions. When the apps speak, again, we'll let them speak. So next slide. So here's the simple thing. I've just given the introduction. We have a lot of prestigious speakers. They're going to talk, and then there's going to be, my cohorts who are going to then tell you about where we're going, where we're at, and then we'll have feedback. So let's start with CS Chang.
Hello. Okay, so I'll just use this. Can you see my screen?
Yes.
Got it. Okay. Well, I'll just use this cursor there. So I am the lead PI for the SciDec Partnership Center for High Fidelity Boundary Plasma Simulation, and also co-lead PI for the ECP WDM High Fidelity Whole Device Modeling at Princeton Plasma Physics Laboratory. So the science we are after in those two centers is basically the ultimate goal is to have a unlimited clean energy reactor to help the building of such a reactor. It's using the highest technology available on Earth at the moment, including computers. In a quasi-steady-state energy-producing magnetic fusion plasma, fusion efficiency is determined basically by the boundary confinement, like the inner wall of a thermos jar. So I normally use this kind of figure. If you think about thermos jar, you have an inner wall that's basically coated with silver or something to confine the heat the best way. But if the temperature is too hot, then still there is a heat going to the outer wall. That's the leak. The difference between the fusion reactor and thermos jar is there is no heat source in thermos jar. It just loses heat and cools down after several hours. In fusion reactor, there's a heat source in here. So the temperature is actually maintained, the gradient is maintained by turbulence, okay? So that's important here. So there are two burning questions, very important questions here. How long can the material wall last against exhaust heat? That means that the either is going to be extremely hot, the plasma. So there is a significant amount of exhaust heat going out to the outer wall. That's material wall in our case. So these are the material wall. And the heat is designed to go all to the diverter. We did not want heat to just damage the whole wall, just damage the diverter wall and which can last for years. And then when we need to, we just change it using some automated system. Okay, so that's what we are doing. The problem is, as you can see from our simulation movie, the plasma, hot plasma, is coming out and hitting only a band of, this is torus, a very narrow band of material wall. There is a big issue. If we don't do anything about it, it may last only 1 second. The machine, this part, red part may last only one second or even milliseconds. That is a huge problem. So that's the problem we're going after. We already have thanks to ADIOS, we already have a simulation result on this. The second one we are after is how good will the plasma confinement be at the boundary? That's the inner wall. I talked about outer wall, that's the material wall. So that's the next page. Due to the time limitation, I will not be able to explain too much in detail, but the second part is the fusion yield is mostly determined by the plasma confinement at the boundary, that's inner boundary. This is what experiments find ubiquitously, actually. Every machine finds this. If the temperature of the plasma at the edge is going to be low enough, just a few hundred degrees, so that the carbon tile, whatever material we use at the edge, can withstand without getting melted, then what's happening is that inside, in your core, there's turbulence reaction going on. It's all determined by turbulence, and that turbulence gives something like profile stiffness in the plasma. So it's a d log dr is about constant. That's turbulence self-organization property. If it's too low here, remember this is log, it can never achieve the efficient fusion reaction temperature. But plasma self-organizes for some mysterious reason previously, raises temperature at the edge up and up. And they actually measured it in detail here what happens. The plasma knows how to make the turbulence quiescent at the edge, just not before reaching the material wall. And it raises the pedestal temperature, we call it as a pedestal. In either, it needs to be like 5 keV to have an efficient fusion reaction, to have an energy production rate 10 times more than what's in there. And understanding will either achieve this. Why is it achieved? That's, and how high this will be is an important critical problem also. But there are other problems. These two are two most critical science we are going after. You can see here from our simulation result, this is normalized to actually density is going down. You can see this either kind of light color in the edge. That's what turbulence is being suppressed in this layer here that's forming inner wall, okay? This was almost a miracle given to us by God, actually, self-organization of plasma. So how do we use how is ADIOS being used to enable
1 minute, yes.
Okay, great. To enable the XCC science. XCC, the same as WDM app, uses up to trillions of Markov particles on summit for a few thousands time steps to study either. If I calculate this, at the moment we do simplify the less number of particles. Data size per time step is ranging from 10 to hundreds terabytes, and per day it's up to hundreds petabytes on summit. And there's no way we can to analyze this with post-processing. ADIOS enabled us actually to have the all this simulation possible starting from huge restart file. Before ADIOS, it was taking an hour for an hour simulation. That was really impossible to get simulation done. Now it's only a few minutes for this restart file. And the physics file cannot be really, we cannot really output the physics analysis file out of this. So we use ADIOS 2 for on-memory real-time streaming data analysis. Compression and visualization is what we do and what we are after. On-memory multi-scale time integration, since these are short time scale, to extend this simulation to experimental time scale is also being pursued via ADIOS 2. It's been a few years. Construction of a digital twin with synthetic diagnostics from simulation for near real-time ADIOS communication with experiments is another goal we have together with the ADIOS team. So just to finish up, how is ADIOS being used to enable WDM app in ECP project? You can see that in the core, there's another gyrokinetic code. And then in the edge, we have the XGC code. We have interface, we couple codes. And there'll be more codes after ECP is done. MHD, heating, energetic particles, wall interactions. All these will be done using ADIOS 2 and coupling framework.
Thank you, CS. Appreciate it. Sorry, I know we're on a tight time. Next up, we have Michael Busman from HZDR Germany. He left a video given it's Germany. Norbert, do you want to play that, please?
Scott, can you play this because I didn't set up the sound as you did?
You got to be kidding me. Okay, hold on.
So somebody else is first.
I will play the video. Just hold it.
Into discovery machines for
you can see it.
Physics. And one of the major goals we're looking at in our group is to understand matter on the fundamental atomistic scale, and especially matter under extreme conditions. And here we see a wonderful simulation on the right of a simple foil that is hit by a high power laser, and that can be used for particle acceleration. So I use a high power laser, very powerful laser, and use it for particle acceleration. And these particle accelerators are pretty small. They're on the range of a few microns rather than being really big machines. And here you see one of our big simulations. We have run these simulations, for example, on the Summit system in the US with almost 28,000 GPUs. And you see it's really running live, and we can interact with it and look at it. And it's quite demanding. We get 8 megawatts of peak power consumption here with such a simulation using the full system. And what you're seeing here is that we're looking at individual particles and can really study them, but the amount of data produced is enormous in this case, as is usual with these HPC simulations. At the same time, we have built a large-scale facility called the Helmholtz International Beamline for Extreme Fields at the European Exascale, which can basically give you atomistic resolution, so the same resolution as you just saw, for studying these things with a large X-ray laser, which you see here, the accelerator that is driving this X-ray laser. And if we use such a facility, we get data from both the experiment and the detectors, but also from the simulations, and have to fuse this together. And that's where ADIOS really comes into play. And the idea is to, first of all, build full digital twins of these experiments, because they're highly complicated in inverting the data we get from these experiments, which is usually scattering data, so not real data that directly shows us the position of all particles, but we basically have to make an inverse Fourier transform, something of this like, from the scattering data. We need to do forward simulations that come as close as possible to the real experiments. And that's where ADIOS comes in first. We need to do a simulation of the X-ray laser, of our high power laser, of the system we're looking at, and of the detectors. So coupling those different simulations together. And that's where ADIOS comes from, using the OpenPMD standard that's set on top of ADIOS to really stream data from simulation to simulation and run several simulations in an HPC system. The next thing is to actually build surrogate models, because at the time of the experiment, we can't use these large-scale simulations. We can use them to plan the experiment, but not really to run those simulations while we're at the experiment, because they're too demanding. We would need a large-scale HPC system. So we built an AI surrogate model of this. And again, we can use ADIOS to stream the data from the large-scale HPC system to the AI system that's learning what this simulation is doing, and then building a much more compact AI surrogate model later on that we can use on standard hardware during the experiment. That gives us reasonably good approximation of what the real simulation would do. And at the same time, we also want to use these AI models to actually infer from the data back to the experiment. So not just finding some by eye some congruence between what the model gives you and what you see in the experiment, but really take the experimental scattering data and go back to the most likely situation we're seeing it. So really inverting this and using the AI model to also invert this. And again, we have to train these AI models with a huge amount of synthetic, but also in experimental data to really do this. And that's where the streaming capabilities and the scalability of ADIOS really come about with us. And in the end, if we can do this, we can finally go back to the very small set of describing parameters compared to the large scale petabyte sized simulation data and experiment data to just infer the describing parameters that describe this very complex scenario. So the initial parameters and the boundary conditions and everything like this, using this AI approach. So we are really going for a large scale data reduction in a very short amount of time. And again, this is where we need those streaming data in the first place to give this in the AI system and then very quickly make a very, very fast reduction. So this is my short overview of how we are using ADIOS here at the Center for Advanced System Understanding at the Helmholtz Center, Dresden-Rossendorf. So we use it for running full digital twins that connect a lot of different simulations. And we also use it as an input to really large scale AI modeling to create surrogate models for experiment, and finally using the streaming data during the real experiment to also stream this within the AI model to invert the data there and understand what is happening physics-wise. So thank you very much for your attention.
Okay, next up, Arvind.
Can you hear me?
Yes.
Here we go. So in a very short while, I'm going to explain what we are trying to do with DeepDriveMD, which is an approach towards getting 100 times faster per simulation performance for complex biological phenomena. So we study protein folding, we study disordered proteins. These are all fairly large systems on which we are trying to do work. And that's actually driven by these motives that you actually have adaptive ensembles that run all the time. So you saw massive simulations in the previous applications. Here we are actually running like optimized simulations on single GPUs, but the data that it is outputting is quite large that needs to be collected, and we need to run some machine learning models on top of them. It's not just one model, but it can be an ensemble of models. It can be different models that are running at different time points and so on. And then you can really think of it as having two phases. One is a learning phase, the other one is the inference phase. So in some sense, this is a streaming application of machine learning and AI methods that eventually allow us to like run as the simulations are running. You learn and you make decisions on the fly to basically say, should I start more simulations or should I continue with the same ones? Of course, the machine learning framework is supported using the Candle infrastructure, which is another ECP project, collaboration with the Shantanu team. And of course, many of these things are very helpful. And does it really help in the real world? Yes, if you were to implement this using just the file system and so on, we can actually see quite a bit of improvement in terms of the sampling. So here are plots that show the absolute timescales in microseconds of that is the amount of simulations that were done. And we look at the explode population of states that were sampled. And it's interesting to see that the Anton trajectories, which take about several microseconds to actually identify the folded state, we can see the same thing within a couple of 100 nanoseconds, which is kind of cool because you are now able to get at least 1 order of magnitude speed up just because you're using a machine learning driven approach to do this. So we showed that this worked in a previous approach. And so this is good, but now we need to take it to a higher state. So ADIOS is actually something that enables us to run these enhanced scalability, especially in the context of streaming AI. And the way we do that is by implementing ADIOS MDS, which allows us to stream the MD simulation data continuously within the context of this learning loop that I just spoke to you about in the previous slide. And the streaming application of ML and AI is kind of running all the time. So there is it's running as if it's an infinite loop and the decisions are made online as the model learns. And we are constantly training or retraining and then allowing the model to evolve over time. So with respect to a file system implementation, we can sort of compare the sorts of benefits we get. Yes, of course, in terms of the sample states, we see the same amount of benefits. We can actually increase the order of magnitude acceleration by about 100 times. And the resource utilization is something where ADIOS actually helps us a lot, which is that you can actually see that many of the resources that are being used, they're not idle, as compared to the file system-based implementation, where many of the resources are actually spending time waiting for data to come in or waiting for more data to be generated and so on. So this enables us to get a faster time to solution from the streaming runs. And where we are enabling that is essentially trying to take it towards more of these extra hardware that is coming. So AI hardware has become a huge thing. And we can actually train on very large batch sets, especially with something like Cerebrus CS1, where you can get nearly 20x times the large batch sizes we really care about. And this effective use of these hardware under continuous resource runs and so on is important. And that enables us to get at least 500 orders of, 500x performance gain in terms of, sampling that we really care. And is basically looking at how the resource is being utilized. You're spending most of the time in actually doing the machine learning, but the simulations are also continuously running. And that helps us push forward on this agenda of saying, how do we accelerate complex biological phenomena at time scales that we would probably never be able to do if it was just a monolithic simulation. So that kind of concludes the overview of how we have been thinking of using ADIOS and where we want to take it further, which is to interface it with emerging hardware architectures, as well as enabling more streaming analysis of the data. Thank you so much.
Thank you so much. And thank you for keeping on time.
No problem.
Next up is Michael Churchill.
Right. Okay, I'm Michael Churchill. I'm a research scientist at the Princeton Plasma Physics Lab, researching magnetic confinement fusion energy. So I'm showing you here an example of the fusion experimental devices that are spread across the world. This is one of the more advanced ones called K-STAR in Korea. You can see these are complex devices that require a lot of different systems and diagnostics in order to get at the best optimized performance so that we can work towards fusion reactors. And you can see here that there's control rooms full of scientists and engineers that monitor and look at the diagnostics and engineering systems of these machines. And this kind of countdown button here shows the time they have until the next plasma discharge that they have. So there's kind of a cycle that I'll show in just a second that scientists and engineers have in between these plasma discharges in order to get information and make decisions for the next plasma discharge. And this is complicated by the fact that there are a lot of different diagnostics that are used on these devices, all with different modalities and different sampling rates. And the physics phenomena that are manifest in these plasmas cover a range of time and spatial scales. So simulations, as C.S. Chang talked about, are heavily used in fusion in order to better understand the plasmas that are generated in these devices and how to optimize them. So, sorry, like I mentioned about the cycle of these devices, you'll typically have what's called an experimental shot, which will last order hundreds of seconds. And often there's just simple automated analysis that's done by these scientists and engineers in these control rooms. And they try to interpret these 1D plots of the various diagnostics and in about 10 or so minutes. And then they need to make decisions on the knobs that they'll turn on the systems and actuators that they have in order to perform the next shot. So we want to enhance this cycle and give scientists and engineers the best information in order to make better decisions for the next shot. So we envision connecting these experimental fusion devices to HPC centers in order to enable more detailed and better analysis of the various diagnostics, and also connecting it with simulations in a time scale that's what we call near real time, such that on this kind of 10 minutes setting, we can get information back to the operators of the machine such that they can do a better setup for the next shot. So how do we use ADIOS with this? ADIOS has capabilities to do data streams over wide area networks. And the protocols that they use within ADIOS enable memory-to-memory data delivery, so you never have to touch the file system. And it's really a fairly simple switch between file systems and direct memory-to-memory transfers over wide area networks. So you can see here at the data generation side, then passing through the ADIOS framework, you have data streams coming over wide area networks that can be then received at some data hub, which can then be fed out for parallel processing. So we've been implementing this for the K-STAR tokamak using a framework that we call Delta that you can find in this GitHub. And Delta uses ADIOS 2's WAN transfer capabilities to transfer data at about 4 gigabits per second from the K-STAR tokamak in Korea over to the Cori supercomputer at NERSC. This is all built on ADIOS 2 Python bindings, as we were trying to have Delta be usable by scientists and adaptable to the various analysis workflows that they have. And Delta allows generic stream processing and uses asynchronous MPI in order to process the data packets as they come in to the Cori supercomputer. And so doing this, we took a typical workflow that scientists had and kind of supercharged it, where running a complete analysis would have taken about 12 hours on a single process for a pretty heavy turbulence diagnostic. And using the streaming over to Cori and with Delta and ADIOS II, we were able to reduce this to about 10 minutes using 6 Cori compute nodes. So that's my presentation. Thanks for listening.
Thank you, Michael. Next up is Andreas Wishnick from University of Western Australia. Given the time, he also wanted to share his video. Let's get that working. Just put a thumbs up.
Hello, everybody.
Let me know if
In
working.
this short presentation, I will show how we've integrated ADIOS II to enable SKA-Scale processing. My name is Andreas Witzenetz, and I'm presenting on behalf of the ICRA Data Intensive Astronomy team and the Gordon Bell Prize finalist team. ICRA is the International Centre for Radio Astronomy Research in Western Australia. Let me first introduce the Square Kilometre Array. The SKA will be one of the few mega science projects of the century. It will consist of 2 radio telescopes, one in Australia, a low frequency telescope, and one in Western and South Africa, a mid frequency telescope. The headquarters will be based in the UK. Phase 1 will realize about 10% of the full SKA by 2028. And the Phase 1 science books consisted of 2 volumes, more than 2,000 pages, 135 chapters, and more than 1,200 authors from 31 countries. Currently, there are 50 member countries in the intergovernmental organization. Construction will begin mid of 2021. In this presentation, I will focus on ADIOS II integration. The SKA-Scale data flow poses a lot of data I/O challenges. Current radio astronomy data processing is mostly consisting of single machines or small clusters nowadays. The backbone of the radio astronomy software is Casacore. So 560,000 lines of code developed over many decades. Up to now, it only supported serial I/O. The measurement set data model, which is underlying this whole reduction system, is based on the so-called Casacore Data Table System and produces tens of files for a table. And that, at the end, will produce millions of files for typical SK observations, potentially up to 100 million files for typical SK2 observation, and means a huge pressure on shared file systems, metadata management systems, and archiving systems. The table on top right shows a comparison between current day radio telescopes and the SK1 low. And the lower part shows a depiction of the CTDS. The ADIOS Storage Manager is trying to parallelize the column layer I/O for Casacore Table Data System. Initially, in 2014, we started preliminary research, which was performed to determine the optical storage backend for parallel I/O for large-scale astronomy data. At that point, ADIOS was selected, and in 2015, a storage manager plugin was designed for the Casacore Table Data System based on ADIOS. That initial implementation achieved parallel I/O at the column layer, mapped the column-based data structure onto variable-based storage backends, and implemented prefetching for table reading. But it was still not on the table layer. The table layer was still serial, and random access was not fully optimized. As you can see, the scalability of the system was already quite nice, and is seen in the plot on the right. In 2018, ADIOS was rewritten from scratch as version 2.0, and we took that opportunity also to re-implement the CTDS for astronomy data. that also optimized some other things like table engine aggregation for small random write operations based on 0MQ. In 2019, the Casacore Table Data System was refined to allow table layer parallel I/O. So that's on the Casacore layer, not on the ADIOS layer. And it was also expanded to from 32-bit to 64-bit to remove the 32-bit limitation for writing very large SK observations. And both of these implementations were optimized to full-scale SK simulations. We've then put that onto the Golden Bell Prize and went to to be a finalist at the end in 2020. And yeah, the key figures of that run on Summit. So 3 hours of runtime almost on the whole Summit computer. That was about 2 times faster than actual SK in terms of data rates. We've produced 27,360 channels instead of the 64K channels for the SK. Produced about 33 billion visibilities a second. That represents 2.6 petabytes of total data flow. The output of the initial ingest was about 112 terabytes and 760 file sets after heavy averaging. And that represents 11 gigabytes per second sustained write rate. That's not a limitation of ADIOS II or anything like that. It's actually the way the processing runs. And we have achieved about a terabyte a second on subsequent runs. Altogether, we have written about 500 trillion visibilities during the whole run. Visibilities are just complex numbers, essentially. And the final image cube after the second stage reduction is only 3.1 gigabytes. So that's an extreme reduction of the data. And that's my presentation. Thanks for.
Scott, you are muted.
Sorry, thanks. Next up is Zihong Lin. Zihong.
Thank you, Scott. Okay, I would discuss the ADIOS in Gyrokinetic Toroidal code GTC for Exa-scale fusion simulation. Integrated simulations of ether burning plasma is required on the Exa-scale level. The simulations of plasma confinement and stability would be needed before each ether experiment, since ignitions in ether relies on self-heating by energetic fusion product, alpha particle. The confinement of energetic particle, EP, is a critical issue for ether. The plasma confinement properties in the new ignition regime of self-heating by alpha particle is one of the most uncertain issues when extrapolating from existing fusion devices to ether. This includes the EP transport by mesoscale, EP instability, we call often eigenmole, and the interactions between EP with the microturbulence responsible for thermal plasma transport and macroscopic magnetohydrodynamic MHD instabilities, potentially leading to the disruption. In order to address those cross-scale interactions, the SciTech ISAP Center initiate the development of integrated simulations of EP turbulence by treating relevant physical processes from micro to macro scales on the same footing. And a gyrokinetic toroidal code, GTC, has been adapted for further development as SciTech ISAP framework The GTC code aim to provide simulation capability based on first principle global integrated simulations for nonlinear interactions of multiple kinetic-MHD processes. This code now has all the important capabilities from the microscopic turbulence to mesoscale energetic particle instability to macroscopic MHD instability. And it can simulate both low frequency and high frequency wave in fusion plasma thanks to a collaborations to develop all these capabilities in a single version of production code that is quite unique in the world fusion community. So it has a large user and developer communities with a broad impact to the fusion research. An example of such cross-scale simulation is the regulations of mesoscale, often eigenmode turbulence by microturbulence. Our GTC simulations first find that often eigenmode excited by the energetic particle would have amplitude and transport level much higher than the experimental observation. However, in the simulations coupling micro and mesoscale, often amplitude and the transport level are greatly reduced to the experimental level because of the zonal flow shearing and the EP scattering by the micro turbulence. The resulting often eigenmode structure and microturbulent intensity agree very well with the experimental measurements in the D3D tokamak. So the mesoscale often eigenmode dominate the electrostatic potential as shown in this toroidal counter plot of electrostatic potential. The microscopic turbulence dominate the density fluctuations, and the microscopic fluctuations, even though having a much smaller amplitude, it has a great effect on the longer wavelengths, often eigenmode, and that led to the reductions of the energetic particle transport by order of magnitudes to the level similar to thermal plasma transport. So the resulting density fluctuations agree very well with the measurements, and the fast ion transport also agree reasonably with the modeling from the experiments data. The most impressive agreement is the often eigenmode mode structure and amplitude. For the first time, we are able to match both mode structures and the absolute amplitude with the electron cyclotron emission measurements of such often eigenmode. So all these simulations require a advanced computational capability. The GTC code has implemented a series of different solvers and parallelizations, including a hierarchy of the domain decompositions and shared memory models using both OpenMP and OpenACC. And the code has been fully optimized on the GPU computers thanks to DOE car project that led to the GTC speed up of about 20 times on 1/5 of the whole summit. And as part of the summit acceptance test, the simulations using physical parameters were able to scale up almost to the whole machine.
Yeah, could you try to finish quickly?
Okay, in 1 minute.
Thank
All
you.
right, so this has been further developed in the site that I said. And I would like to highlight that GTC is the first application code for ADIOS, thanks to my privilege of working with Scott back at the time at Princeton. So this is what recent ADIOS team that helped GTC, and I borrowed one slide from Scott's
Thank you, Zihong. Let's quickly go over to Wenji.
Yep.
Go ahead. Thank you.
Okay. Okay, so I'm a postdoc from the Princeton Geoscience Department. So what we're trying to do is using the seismic tomography to image the Earth's inner structure. So the seismic tomography is a kind of tool used to inverse the physical parameters of the inner structure of the Earth that governs the wave equation. So resulting tomography models reveal quite very heterogeneous structure from the surface down to the common boundary. And this depth range is quite difficult to approach in other disciplines such as mineral physics or geology. So our goal is really to try to provide a better, higher resolution image of the inner structure of the Earth, and then to facilitate our understanding of the Earth through, for example, other subjects such as geodynamics and geochemistry. So the simulation on the right-hand side shows you the simulation we made in collaboration with the visualization team from Oak Ridge. And the orange colors here really means the slow velocities within the Earth. So you can see there's you can see the top and the common boundary, lower boundary is the common boundary, and there's a huge, we call it plumes, which is the slow velocities arising from the common boundary, and those flows will will dramatically change the dynamics of the Earth in a very long term, given 100 million years. So how we achieve this? So basically collect the seismic data generated by natural earthquakes. We use some optimization technique to allow our model to match those observed data. So back into quite old times, we got our first generation model as M15 model on Titan, and then in the summit we basically obtained our second generation model and M25. So it's basically a 25 iteration of nonlinear optimization, and our newest model contains about 1,500 earthquakes. Let's going to dive into a little detail about the global geotomography and our inversion workflow. So the figure on the left shows you a kind of a demo figure for the spectral finite element mesh of the globe. So we basically partition the Earth, the globe, into different elements, and then we load them into different CPU cores or GPU cores to finish the computation task. The degree of freedom of our current resolution is about 10 billion. So it's about, for each time step, we're going to calculate the wave equation on about 10 billion degree freedom models. The figure on the right shows you the kind of workflow. So we started from a certain number of earthquakes. We finished the forward simulation based on the mesh on the left-hand side. We computed synthetic data, and after a bunch of data processing and measurements, we create some measurements and backfeed into the ADIOS solution, and this will create the give you the kernels, and then the kernels will be further to be translated to the gradient, and we'll update the model. So the ADIOS really placing when we have a very key step between the forward simulation and ADIOS simulation is we need to dump the wave field. We need to save the wave field snapshots between, after the forward simulation, and then those snapshots will be feed back into the second stage, the ADIOS simulation, when we want to reconstruct the backward wave field. So you can image that we are saving, constantly dumping the wave field files to the disk for like 100 time steps. And this, given our current resolution, each earthquake will generate about 1 terabyte of wave field snapshots. And given our current data sets, about 2,000 earthquakes, it's about 2 petabytes of files we have to dump into the file system and then be read back into the ADIOS simulations. So some performance metric about ADIOS on Summit. So we finished a few different kind of tests. The first one is stress test. So we perform about 50 earthquakes. It takes about 80% of the Summit computing power. And in total, it dumps about 250 terabytes of files into the file system. And we compile different methods for the ADIOS 1 version. So you can see the POSIX and MPI grid give similar performance. And then recently we just migrate to ADIOS 2. And we also did test using the BP3 and BP4 as a backend engine. And you can see there's still quite a lot of improvements given we migrate from version 1 to ADIOS version 2. And the last one is some metric about a performance metric of the real production case on Summit. So currently for a most recent model, we have about 2,000 earthquakes. Each earthquake will generate 1 terabyte of wave field snapshots. And in total, it will dump more than 2 petabytes of wave field snapshots into a disk. The total simulation will use about 2,560 Summit nodes, more than 50% of the power. And the total running time for the forward simulation is about 3.45 hours. This step includes the saving all the snapshots to disk. And I/O, based on our measurements, takes about 25% to 30% of the overall running time in forward calculation. And in the ADIOS simulation, which is essentially backward calculation, the total computation takes about 4.5 hours, but this step only involves reading the snapshots. It's kind of less demanding as the last step, which we dump the files. So I think overall, we achieved great performance of ADIOS. Our collaboration with the ADIOS team started from a long time ago. The time when we used Titan, and then on Summit we continue using the improvements, making improvements on the surface, and this is the performance metric you can see. And I think overall ADIOS really help us to save our I/O times. Thank you.
Thank you. Next up, I see Axel, although I see the video of Jayesh, so I don't know. I'm okay, whoever goes next, but someone go next. Axel?
Oh. You have a video of me. You can
I don't have it quickly available. Hold on. Gotta, that's okay. No, I got it. Just, hold it. Share. Work, share.
Welcome to an overview of the science case of our BECs and how we use ADIOS to achieve these highlights. Particle accelerators are an essential tool in modern life. They are used in medicine, industry, national security, and are essential for discovery sciences. Yet, the opportunity could be much bigger if we could reduce the size and the cost of particle accelerators to a smaller level. For that reason, we research at Berkeley Lab plasma accelerators that can shrink potentially the size of accelerators by orders of magnitude. Specifically, we are driving a short driver, such as a laser pulse, through a long plasma and accelerate particle beams through stages in the future to achieve really high energies. In these particle accelerators that are driven by wake fields, we have to resolve really small features that we show in the slide here over many time steps and resolve them with many grid cells and macroparticles. For that reason, in the ECP project, the new particle cell code WARP-X code was conceived that is based on AMRX, builds on newest architectures, especially GPUs, and combines the most advanced algorithms. Advanced algorithms are essential for us, specifically to achieve long acceleration lengths. So for example, we implemented and invented actually algorithms that make it possible to go through acceleration lengths that are meter long, although we are resolving micrometer scale phenomena. We implement very general algorithms such as mesh refinement that have not been seen yet actually for electromagnetic PIC and don't work well out of the box for those due to reflections and instabilities, and we conceive algorithms for this and achieve high stability in our research with that. We specifically also research field solvers that are used for AMR but also for non-AMR simulations, and research high stability and reduced physics to achieve fast simulations for our science cases. WARP-X, although it is conceived for plasma acceleration, has yet seen many more applications, and here's a small example from our own users as well as collaborators. To give you an overview about the data size that we're talking about, on the simulation scale of WARP-X or generally electromagnetic particle cell modeling on summit scale, we're talking about the order of 10 to the 11 to 10 to the 13 particles, 10 to the 11 grid cells, updates in the range of 5 to 20 Hertz, and up to roughly 100,000 time steps, which is quite a lot of data. So we can think about like a petabyte per simulation easily and more. In recent work with the ADIOS II team, we improved the write performance of WARP-X. We started from already a pretty strong baseline, which was already using subfiles on a parallel file system to achieve fast writes. And what we compare on the left-hand side is an implementation of plot files that uses the subfile method compared to ADIOS BP groups where you create subfiles per rank and step. As we found out, creating more and more files over the course of simulation is actually creating quite some overhead, and so we mitigated this problem by appending to existing files and using the implemented ADIOS steps, which will be the next update of this iteration, to achieve higher write performance. At the same time, we implemented a method to use ADIOS variables efficiently to implement the sparsity and structured MR meshes. On top of that, we made use of aggregation that you can see on the right hand side, and we saw that depending actually on cluster and also actually on the size of the simulation, aggregation per rank and per node can give you better performance for this and reduce the file numbers by a factor of 6. Why do we want to reduce this? Well, writing fast is one part, but actually the real challenge comes in reading. And what we find out is that there is actually not one data layout that can actually bridge and address all needs that we have. Specifically, with mesh refinement and sophisticated load balancing in WARP-X and AMRX, as you can see on the left-hand side, we can create quite a lot of chunks that we write out to disk and that go into zap files. And realistic read patterns that we visualize here in the middle can actually create totally different requirements for data layouts to be efficient. So for example, a layout that reads perfectly in alignment order can be perfect for logically contiguous data, to read it once and go straight through the data. But if you read actually a slice in the opposite directions, the situation of read performance looks totally different. And what we found out is that, well, we can actually research and try to bridge these gaps by doing a merging algorithm that tries to find close by groups and reducing them to medium-sized chunks that are more efficient, and so we can find somewhere a middle ground between the two worlds. What happened to this? Well, we looked into this in more detail in quite a lot of read patterns that are used in reality, and just taking one example here, what we show you here is that something that looks great actually in serial reads, starting at one processor here and logically contiguous data, can look totally different if you actually do parallel post-processing of that, and actually the read time goes really up in this case. And so what we found is that in combination with parallel reads and using a data layout that uses chunking and subfiling but merging to mitigate the gap between the two, we can actually get pretty decent read performance for realistic I/O patterns. This is one step of the many things that we're exploring with ADIOS. We are going further in tuning MR fields, and we're looking into pipelines and data reduction, but this is something for a different topic. We're sharing our results by standardizing our domain-specific needs in an open standard for particle mesh data, which is a schema that can be implemented in ADIOS 2. And as you can see here in this long list of partners in the so-called OpenPMD project, we have strong national and international partners that make use of that and can thus also tap into the achievements that they get from ADIOS. We implement this work into strong partner and lighthouse projects such as the WARP-X code that I'm representing today, but also codes like Pick-on-GPU, which is an OLCF car project, and was also actually the code of my PhD project that you can see on the right hand side, with which we created already great science achievements on Titan at the time. Just recently, we also used these libraries that we implemented here to implement a new parallel reader that uses the patterns that I just mentioned in ParaView to give all the codes and partners in this collaboration the ability to do efficient 3D visualization in parallel of that. And we're exploring more and more novel analysis routines, specifically in the Python world, such as Dask, that can scale to full sizes of clusters.
Okay, Jayesh, you are next.
Jayesh, go ahead.
Thank you, Scott. Can you see my slides now?
Yes.
Okay, thank you. Hi, my name is Jayesh Krishna. I'm a senior software developer at Argonne National Lab. Today, I'll be discussing our experience using ADIOS in the E3SM MMF project. The energy Exa-scale Earth system model is a state-of-science Earth system model with multiple model components to simulate the different components of the Earth system, like the atmosphere, ocean, land, rivers, land ice, sea ice. Many of these model components use unstructured grids, like the cube-sphere grid used by the spectral element atmosphere dynamical core component that's shown here, or the Voronoi meshes used by the MPAS ocean model. And the models also frequently use regional refinement in the grids. In the E3SM MMF project, we are looking at improving certain subgrid scale processes in E3SM that has been historically parameterized poorly in climate models. Specifically, we would like to resolve convective storms, like shown in the figure on the left above. To achieve that, we are using the, in the MMF project, we are using the multi-scale modeling approach and running multiple instances of the high resolution cloud resolving model on each grid cell in E3SM. This approach is shown in the figure on the left below. And this allows us to get an improved parameterization of the clouds, and also allows us to use the newer architectures much more effectively. And this parameterization of clouds has been historically a source of uncertainty in climate models. We find that typically at these high resolutions that we need to run to simulate phenomena like convective storms, I/O is frequently the bottleneck. All E3SM components use the Scorpio library for reading input data and writing model output to the file system. The library provides an API for describing the data layout in the model and for reading and writing data out. The library also provides algorithms to rearrange the data across MPI processes. This is sometimes required to improve the performance with certain lower level I/O libraries. and also provide some caching capabilities. The E3SM model component typically writes restarts and history files during a simulation run. The amount of data, as you can imagine, depends on the configuration of the runs, like the resolution, the variables written out, etc. A typical ultra-high resolution simulation with a resolution of about 3 kilometers generates hundreds of variables at 4.5 terabytes per simulated day. We have worked with the ADIOS team now to add support for ADIOS in Scorpio. And we have tried many E3SM simulations with ADIOS now. Since our post-processing tools still rely on netcdf files, so we have worked with the ADIOS team to develop a conversion tool that would convert the ADIOS BP files into a single netcdf file in a post-processing step. On the right, you can see the I/O performance of E3SM with ADIOS 2. On the top, the results are from Corey, and the results at the bottom are from Summit. As you can see, we have tried atmosphere, land, and ocean simulations with multiple resolutions and configurations using ADIOS. And depending on the system and configuration, we get a 4 to 16 times performance compared with the next fastest library that we use. That's the pnetcdf, the parallel netcdf library. The parallel netcdf library provides us the best I/O performance when writing data into a single shared netcdf file. But with ADIOS, we are getting much higher performance writing to ADIOS BP files. For example, on Summit, for one of the recent runs that we did with ultra high resolution simulations, that's about 3 kilometer resolution. We get about 300 gigabytes per second I/O write bandwidth when running on about 300 Summit nodes. With the improved I/O performance of ADIOS, we'll be able to do more high-res runs and output more data and advanced climate science. About ongoing and future work, currently we're working with the ADIOS team to support reading back the ADIOS data and adding support for BP4, the newer file format, and improving the performance of the netcdf conversion tool. We are also working on integrating the post-processing required for converting ADIOS files to netcdf into the E3SM workflow. We are also exploring how we can leverage other features in ADIOS like compression and in situ analysis for E3SM simulations. Finally, I would like to quickly acknowledge that most of the work discussed here was done by Tarsin at Stony Brook, and Norbert at Oak Ridge, and Dan Ching at ANL.
Okay, thank you, Jayesh.
Thank you for your time.
I realize the complexity of getting this on time, and we've had a lot of wonderful talks. And what we're going to do is a slight adjustment in our agenda, which is I'd like to take a pause of where you guys, if the other video from the other speakers can come on, and I'm asking for questions or requests. And after that, we'll spend a few minutes telling you some internals about what's going on with ADIOS, but just to make sure that we have time for questions or requests or complaints. In either case, that would be great. So could I get just one brave person to just unmute and have something? So do we have anyone to just ask one question or have a request?
Hi, Scott. I'm Wenjie from the Princeton Geoscience Department. Actually, I have a question. So I recently opened, we recently migrated to ADIOS 2. And actually, I tried to use the ADIOS 2 Python interface to read back the, the ADIOS 1 file, and it just works perfect. I'm little, Python is becoming, more and more popular in the data analysis domain. And I'm wondering, do you have any comments or vision when you talk about the future development and also the backward compatibility of a Python interface? For ADIOS 1, I think that Python interface is not quite as good as ADIOS 2. I think you guys already, yeah.
No, that's correct. And if I think of Arvind, your workflow, that's Python mostly, I would think. So what I'm saying is Python and C++ are the first-class citizens here. Fortran is important, but again, it's Python is our big one for reading, for example, and C++. Norbert, comments on Python?
All right, so Axel, you saw Axel's presentation. He takes a lot of care of making ADIOS tested and work on Python. And as he showed, parallel Python is the future to go. Serial reading is still not the best, so right. Thank you, Axel, for all the help to make it.
Yeah, especially when he said he may be somewhere else. Thank you, Axel.
You're welcome. Thank you.
Which is an apps person doing it, which is amazing. Okay, someone someone was on here ready to ask the question.
Yes, Aswata.
Yes, I had a quick question for Wenjin, actually. This is not about ADIOS, it's about your code. Are you, I wasn't quite sure, were you just doing inversion or were you also doing some forward modeling?
Question for me, Wenjie?
Yeah.
Oh, so in our workflow, we're doing both the forward simulation, which I think is calculating some synthetic data. And then we're also doing some inversion. I mean, we compile the match between the synthetic data and observed data. We throw the misfit back into our inversion machine, and then we calculate the gradients and we update the model. So it's two things, the whole workflow glued the two things together.
Thank you.
Yep, thank you.
Okay. Any other questions? If not, we're going to hear from Norbert next. So that's a threat. So
yes, it will be much more boring after all these great presentations.
okay, so please ask questions whenever you want. Norbert, it's all you right now.
I'm trying to share my screen. Right, so you see a boring picture. Before all these great presentations, I usually show a graph and say, okay, we can achieve over 2 terabytes a second doing an application with one type of I/O, and that's what showing how ADIOS is so awesome. But this is just one specific thing to achieve, and there is more to I/O for an application, as you saw in these presentations. And to show that, I want to focus on the GTC story right now and tell you what we learned on the way and what we are going next. So when GTC was a CPU code, and it's used POSIX.io and NetCDF.io to write all kind of data out, diagnostics and snapshot and 3D field data and doing the checkpoint restarts. And then when they did this 20x speed up on Summit for the GPUs, the I/O became the bottleneck. And so ADIOS addresses, or we addressed with ADIOS all kinds of I/O in GTC, not just checkpointing. There are different issues here. The one is like the snapshot. The snapshot is was a simple Fortran statement to write out some small data, a few kilobytes or megabytes every step, but creating a new file every single step, because this is the most important to track running applications and look into it. So whoever developed this decided to create a new file every step, but it's a small file. And then the field data is, they use netcdf because they need some parallel IO, and every slices of the torus writes a single file. So there are 32 files written every step, and then writing every 10 simulation step, they write out one output step. This is a netcdf file. As usual, users don't dare to risk writing into a single output, because if the application dies in the middle, you lose all your data, right? And then the checkpointing is every process just dumps its own file. It's very simple to write, runs great until you really scale your application on Summit, and then at some point your performance will tank. So using ADIOS for these kind of tasks, you can use for all kinds of IO, like writing out the snapshot in a single file, open it, write, dump whenever you need it, and then close it. Single process writing the IO, done. You can write a parallel IO and write all the field data in a single, all the 32 planes, every process, thousands of processes writing into a single data set, and then every step writing into that same data set. That's what Axel was pointing out. That's what helps WarpX as well a lot. And then for checkpoint is the same thing. Don't create every one file per process. It doesn't scale. Doing a parallel IO properly just to write one output data set using the ADIOS API, you don't need to focus on the number of files. No tricks. One output and then done with it. And then ADIOS does subfiles under the hood to optimize for the bandwidth of the file system. And then in this case, 512 nodes produces 500 files on the disk, but you see the whole thing as once. Why is this important? Is that the achievement was that at GTC, when it achieved that 20x improvement on the GPU optimizations, and that was many years of effort, then you see the IO becomes like 30% overhead for this application. But changing all of the IO, all different kind of IO into ADIOS decreased this enormously. It's still 10 minutes to write those hundreds of terabytes of data on Summit, so it's still a big number, 10 minutes, but compared to what it was, it looks pretty good. Now, I don't have a detail of which affected more the IO here. We know that the snapshot took 40 minutes for these 10,000 output steps. No one would guess that, oh, that's just happening on Summit. Well, it does. So why not just, you can trust ADIOS, and you can put all your data in an application into ADIOS, and then it will work for all kinds of situations. That's the basic message, and what we learned from ADIOS is that using aggregation properly on a file system, tailoring the performance of the IO library to the capability of the file system is the #1 thing that you have to focus on. Second one, try to limit the number of files by appending steps into one output step. And then that will avoid the bottleneck caused by the metadata server on the file system. And on the side, you can trust ADIOS not to corrupt your data. It's a log format. Data is only appended if the application crashes in the middle of the run. All your previous steps are intact, and you can read it even if it dies in the middle of the output step, or of the last one when it crashes. The same story is with the reading. What we learned is that at scale, the logically contiguous file format does not compete, because it poses a big bottleneck to write it from multiple processes. That's the blue color on both charts. The top one is the writing, the bottom one is the reading. Using chunking up the data and then using subfiles gives you the scalability that can keep up with the file system capability even at large scale. And that's what all these applications that we're presenting are enjoying by using ADIOS. On the read side, however, there are difficulties with reading back all these blocks. And so, as Axel pointed out, reading in parallel, even if it's just a few number of processes, it gives you a good concurrency and parallelization of the reading performance. And nowadays, a single node has 16, 32, more 64 cores, so it's natural to use multiple processes to read in the data. And if you think of that way, even if you run a Python script and use NumPy to store your data, why do you want to just run a single process? You can run many processes and read in that data, right? So that's the lesson what we have today. So aggregation and appending time steps into one data set is the two things that you can do to achieve those big numbers that you saw in today's presentations. What we know our next bottlenecks. We always have bottlenecks, right? We fix the big ones, then we run into other bottlenecks. So we have two bottlenecks that we are working on to fix this year. One is that ADIOS, as it handles its own metadata to track all these blocks in the file so that you can read it back from. There are lots of variables, lots of processes. There is a lot of small blocks, and all that metadata is managed in some way. Unfortunately, the cost of handling this increases today with the number of variables, with the number of processes, the number of steps, the number of blocks that each process writes. So we are working on that to redesign how we deal with the metadata and decrease this problem. So not to be a linear increase and make metadata handling scaling just as we did the data writing part as scaling. And so we know that the two applications that suffering from this, the others, most applications are fine. They have those great performance, but WarpX has so many blocks, like 10 blocks per process per variable. So you have 1 million blocks easily. And E3SME is one which has lots of variables. It's 500 and 1,000 variable in an output step. So they are suffering most of this. The other bottleneck is that it can happen if an application doesn't know how many variables it will going to write in a step, and it doesn't know how much data it has to write it, and they just naively use the ADIOS API, it can lead to a lot of memory reallocations inside the ADIOS engine. And that shows up as a bottleneck in Axel's other favorite application, the Pico and GPU, that was Michael Bussmann was kindly not to mention, but we know that's the other bottleneck that we are facing at large scale. So this is the two topics that we are looking at and trying to fix it with the next version of our.
So Norbert, thanks. What I thought, and I don't mean to be a pain to Greg. I tried to write him, but Chuck Atkins, who's Kitware, is our software engineer, and if he could just say like a couple words before Greg talks about staging. We have 7 minutes, so you could understand the challenge that we have. And Chuck, can you just tell us quickly in your own words, unmute and show us the video of you?
Sure. Yeah, I did want to just kind of spend a few minutes to kind of tell you about some of the build and test infrastructure we have in ADIOS that kind of goes to the underpinnings of kind of why ADIOS is kind of something that's stable that you can use at scale and rely on. We currently, we're using the, I guess our build and test infrastructure right now is built on top of CMake, CTest, and CDash. We have.
You are not sharing, Chuck.
I'm sorry?
Not sharing your screen.
I wasn't, okay, here we go. Okay, it's built on top of CMake, CTest, and CDash. Using kind of a modern target-centric CMake. We support both serial and API flavors of ADIOS in the same installation. That's particularly useful for applications that have kind of a front-end component and a back-end component, where you might have like a serial front-end component and a parallel distributed back-end component, and not needing two separate installations of ADIOS. We've got, we use a variety of different testing infrastructures for fine-grain and coarse-grain testing. Each one of our builds that we run in our workflow for development has up to 1,500 tests that we run on it on every pull request, and that's per build. And we run close to 28 different builds for every pull request. Our continuous integration is built on top of really a variety of public cloud CI infrastructure using GitHub Actions, Azure Pipelines, Circle CI, a whole slew of things. We're testing a variety of GCC versions, PGI versions, Intel Parallel Studio. We even have the IBM XL compilers on Power 8, Microsoft Visual Studio, Apple Clang. All of these are tested on public CI infrastructure on every single pull request. We have dynamic analysis with kind of testing for undefined behavior, memory.
So Chuck,
yeah,
I'm going to have to cut you because
nope.
Somehow we got to fit everyone in 4 minutes.
Fine.
The point, Chuck, is the reason why, like, as people are doing this, even with experiments, is things are extremely reliable. So having software engineers like Chuck are invaluable. So Chuck should ask for a raise. Okay, let's continue. So Greg, we're going to give you 2 minutes.
Hey, Norbert, you sharing my slides?
Okay. Yeah, I'm taking a few seconds.
Start talking.
Okay, so I'm here to talk about data staging. And while others have at least briefly touched on this earlier, let me specifically define what we mean by that. ADIOS originated life as a file system, a file IO system. A lot of folks are still using it that way. By data staging, we're talking about the simple concept of connecting the readers and the writers directly together and avoiding the file system. That's an easy thing to say, but when it comes to actually accomplishing this efficiently, that's a lot more complex. In particular, that simple statement leaves a lot of things undefined. Are the readers and the writers co-located? Are they in the same job, the same cluster, different continents? Is the exchange synchronous or asynchronous? Is there queuing involved? How does this all work? So basically in ADIOS, the details of how the data is manipulated once you get past the API are largely encapsulated in the ADIOS engines. And ADIOS has a number of staging engines that tend to answer these questions differently. So I can talk here very, very briefly about 2 of those engines. The first is SST. SST is our most general staging engine, with the idea that if you can do it in files, you ought to be able to do it with SST too, whether that's writing from thousands of ranks to thousands of ranks or writing from thousands of ranks to just a couple. If you can have a large fan-in, we can do full M by N compression. We can have multiple simultaneous streams from a job, multiple readers on a single stream. Readers can come and go. We have multiple data transports. We have multiple time-step consumption modes, etc. SST, this is a code from a CS Chang example with the whole device modeling. And if you look at the link display there, I think you'll see SST in about 7 places, including SOS Flow, which is a monitoring system based on University of Oregon's Tau that uses SST for connections. Another engine that we have is DataMan, which answers some of these questions slightly differently. In particular, DataMan relaxes its requirement to do complete M by N and lets you have different reliability requirements. Here we use DataMan for K-star and do stuff intercontinentally using 0MQ. In summary, if you've got a staging application, talk to us. We can help you figure out which engine to use or improve our engines if you're not getting good performance on the ones we've got. Thanks.
And finally, we have Jumin. I'm sorry, Jumin, you have less than a minute if we keep on time, maybe a minute. Can you just say a couple words about AMR?
Okay, so I'm going to.
Remember, you have less than a minute.
Okay, so I'm going to just talk briefly about AMR, so I'll skip all the other slides. So for AMR, what we're using is we're using the OpenPMD API to store the AMR data for WebEx. And you can see here on the left, that's a course example, a course level example. So there's data with 2048 cubed mesh. And at second level, the mesh, all the meshes are refined, every direction refined by factor of 2. And so we store the general dimension, and as people who work with mesh refinement knows that only part of the region is refined. So what we do is we only store the part of the data that's effective in the refined region. And here's a comparison that on coarse level, we store everything, the whole region. And then on the refined level, we only store the refined region, which is about 10% of the original one. And it reflected in the in the storage size, file size. So this is the performance result from the course level, and there's two different setups for WAPEX, and this is the files goes up to 100 something terabytes, and then here's the reading performance for loading up the files, and here's a preliminary run for using AirMax with one refined level using WAPEX. And we can see it's it's a summit number, and it's sort of compatible with the course level, a little bit slower.
So Jimin, thank you. Yeah. And for all the participants and speakers, if we had more time, it would be great to have a much longer discussion. But I want to thank everyone. I know we're over time. I really appreciate all you guys. Yes, Axel showing his face. So thank you, Axel, for, I know you must have been tired after your plenary with John Luke. CS, thank you. I've been working with CS for like 80 years, Zihong a little longer than that. So we were all young when we started. But I think we've done a lot together. So the point again, and I hope it was clear here, we are completely driven from the applications. This is just not ADIOS's IO and what we care about. So come to us if you're an application, or if you're a software developer and you think you have something that could fit in ADIOS. I mean, Axel wrote from his perspective, and they've developed a lot that has gone into ADIOS. So I think it's great synergy. I want to thank everyone for sticking the entire time. I know we're out of time, so thank you again.
Thank you, Scott.
Thank you, everyone.
Thanks, Scott. Thank you.
Okay, bye.
Thank you, Scott. Thank you. See you,
everyone.
Bye.
All right.